two copies of vector representations and the symmetric power. Algebra, I want to conclude that, make it more precise, and also correct some mistakes in the formulas. And then I will talk about the fundamental representations, and then explain the Howe duality, the classical Howe duality, the classical case. And tomorrow I will do the quantum case. Okay, so the observation of Jimbo is that you have an R matrix for the vector representation, so you have vector representation. Of SLN, and then you have an R matrix, maybe R check matrix, composition with the transposition of Z, and R check was up to some factor, scalar factor. It was T minus Q, so ZT minus T inverse. And this T obeys this equation. I think the signs were wrong the last time. But in the exercise session you will look at this again, and I hope the formulas are correct on the exercise sheet. Okay, so this was a story, and then we noticed that it means that T has eigenvalues Q and Q inverse. So now usually this R matrix is invertible, but for special values of Z it is not. Namely, if you take R hat of Q squared, this is something as Q squared T minus 1. And here actually one should, no, I think this is correct. And so this is equal to 0. So it is equal to 0 on the eigenspace. So okay, so here we have eigenspaces, which I define to be wedge Q to Q of V. And
what does the Q mean?
What is Q?
This Q. Wedge Q.
Q deformed. It means Q deformed. Is this Q?
I know, but
the definition of it. So the eigenspace is for the eigenvalue Q inverse. And so eigenspaces. So this is for Q inverse, and S2QV for Q.
But how are
it minus Q inverse?
Yeah, minus Q inverse.
So that's the definition of those wedge 2 and S2.
These are two subspaces which if Q equal to 1, these are the skew symmetric tensor and the symmetric tensors. And now
and the definition. Ah, okay. I see. Okay.
And so now, if Q is if T if you are on an eigenspace of T with eigenvalue Q minus Q inverse, you will get 0. So this will be on 1 to Q, and R check of Q to the minus 2 is something will be 0 on this other eigenspace. So it will project out the symmetric tensors. And here I should say reg, because actually this is infinity, the coefficient. So you have to really take the residue. And then, so what happens then? Then you have this exact sequence. and it's periodic, right? So you can go back. It's actually exact. So the composition is 0 so for right. And so then you can realize the so this was for the finite. So these are kind of analogs of skew-symmetric and symmetric tensors for the finite dimensional algebras. But now here we see that these are a homomorphism of representations of UQ of SRN. The kernel and the image are sub-representations, which I can define as, again, the exterior power with spectral parameter or symmetric power. So then I can define wedge QV of Z to be the kernel of a check of squared, and again definition if you like, but it's a sub-representation of whatever of this, and the symmetric power at evaluation point Z as the kernel of R hat of Q to the minus 2. One of the two is regularized. Okay, so this realizes these representations as sub representations of these tensor products, but realize in different tensor products. But you can also, since this is an exact sequence, you can realize them as quotients, and then you have some exact sequences that is a sub-representation of the square Z. So it's both a represent and you have the sub-representation of the square Z. So you can realize this representation both as sub-representation and as quotients, but in different tensor products with different spectral.
Is there Q missing as a subscript?
Yes.
Sorry, Giovanni, do you mind just putting up the boards just a quick second so we can turn off the screen underneath?
Should I raise it?
Put the other one up. Thanks, sorry. It should turn off, yeah, perfect, thank you.
Right, and actually these sequences are not split, so the representation is not a direct sum of these two, but so the category is not semi-simple. Okay, so and now so let me say, so this generalizes actually, and so let me talk about just a few words about fundamental representations. And here I should say that there is a different terminology in mathematics and physics. Fundamental representation in physics, as we heard yesterday, means the vector representation. So, but here I would like to use the mathematical definition with its representation with fundamental highest weights. And what does it mean? So we saw last time that V lambda, so for each partition, lambda 1, of integers, we have a representation V lambda, the highest weight. Representation V lambda. So these lambdas, these partitions, form a cone in the n tuples, or minus 1 tuples, and this cone is general. So P plus maybe is a set of partitions. So P plus is really is spanned by, maybe I use a Bourbaki terminology. Is spanned by these fundamental weights. This is n minus 1. They are called pi. So it's not pi. The fundamental weights and the other partition, 1 larger than 1. And here this is the Eigen space. And you can write any partition as sum of these with non-negative integer coefficients, and so of SLN, and this V lambda, and so the fundamental, so it's useful also to draw these partitions as Yang diagrams. When you draw them in this way, so this would be lambda 1, this would be lambda 2, and so on, boxes. And so the fundamental weights omega I would be these column diagrams of length I. And the corresponding highest weight representations are generalization of this wedge 2, so there will be wedge I, wedge Q I of V, and this is the kernel of some projection that you can construct out of T, but I will give later a more explicit representation. So this will be generalizations, and so they are generated. So these are kind of Q symmetric. Tensors. So in the exercises we will do it explicitly for n equal to 2. And so they are generated, so they have a highest weight vector something like E1, E2, maybe. So it would be and then you have plus some permutations with powers of Q of these first basis vectors, and so the weight is, if you compute the weight, it is exactly pi I. Okay, so this is this highest weight theory. So so now let me talk about, so for Q equal to 1 is just E1 up to EI. This is a highest weight vector. You can check that this is killed by the what I also called EI, namely the EI I plus 1 matrix units. Okay, so so let me talk about Howe duality now. In the classical case for Q equal to 1. So this is sometimes called skew Howe duality. So this is in a paper of Howe of 1995. And I think, so Howe also writes that it is basically a consequence of a result of Constant in 1961. Computed some cohomology of parabolic subgroups. But I will describe it in an elementary way. So, so again, now so for this it is nice to take GLN. instead of SLN. Take the group GLN, and V is a, and you take V, again, the fundamental representations. And so recall first the Shurval duality. This is, we described that, maybe on Tuesday, or if you take the product of small n copies, then you have two actions. You have the action of GLN, and you have the action of the symmetric group of Sn, because you can permute the factors, and then you can decompose it into irreducible representation for both, and today I will be slightly more precise. So you have here the partitions with in at most. So maybe I will write diagrams. It's more intuitive. Diagram with less than n-1 rows and
boxes, or?
And then boxes. And then you have V lambda times, I don't know, E lambda. So this is an irreducible highest weight representation. Of GLN, and this is an irreducible representation, which are also labeled by Young diagram of the symmetric group. And right. So so now the question is, so from our point of view, is we generalize the Shurval duality if you have a product we also want to decompose it in irreducible representations, and so that is a question. And now, so it's useful to do the general case, maybe. So instead, we go to the whole exterior algebra. So this wedge V is exterior algebra. And one way to look at it, so in the exercise session you get the professional way to do it with universal properties. But here I want to be kind of concrete, and I want to see this as non-commutative or skew-commutative polynomials in n variables. So these theta 1 up to theta n are a basis of Cn, and so you take polynomials in this, but modulo skew symmetric polynomials, so you obey this kind of relations. So you have a basis which is theta I1, theta Ik. And this is a direct sum of the degree of the polynomial. So, and maybe I should remark that lambda, so these lambda k are fundamental representations for with k from 0 to n minus 1 for SLN. And then you also have the top one, which is a determinant representation. Okay, it's one dimension. And so maybe fundamental is a from 1 to n minus 1, and wedge 0 is just, by definition, if you like, the trivial representation. Okay, so you have that. Right, now the observation, very simple observation Howe is that if you take, so before that, so you have this simple rule that if you have two vector spaces, then the direct sum of the exterior algebra of the direct sum of the vector spaces is isomorphic to the tensor product of this skew commutative algebra. So this is a tensor product of Weyl commutative algebras, which means that you have to put the signs. So, but Howe is interested not in the direct sum, but in the tensor product of the two representations. And now on this tensor product, first of all, so the theorem of Howe is that on this tensor product, you have an action. So no, what is clear is that you have an action of GLN and GLF. So let's suppose V is Cn and W is Cn. Then here we have an action of GLN and an action of GLM and small n. Should use another letter, but now I have capital N and small n, and they commute. And the theorem of Howe, of constant or somebody, is that this is a multiplicity-free action. Namely, you have two groups which act just like here, and if you decompose it into irreducible representations, each representation occurs exactly once for each of the groups. Or the other way to say that is same thing is that that you have two actions which are the commutant of each other. If you take the group algebra, the commutant.
Maybe I'm slightly confused. Are you saying that it's multiplicity free for the action of the product of two groups?
Yes. Right.
And but also you're saying that for each representation of GLN, it will only occur in the pair with only one representation of GL small n. So that's a kind of further.
It's a further statement, yes. Like here.
And this is always the case for any n and.
Yeah, right. I think so. Yeah, I think it is yes for any.
And then what's the correspondence? This establishes the correspondence between representations.
Right.
Of what GL capital N and GL small n, what's the correspondence?
Right. I will come to that. Mm-hmm. So this is the first statement. But maybe the statement is that so the theorem is that that this wedge isomorphic to the direct sum, and I will have over certain that's the correspondence. The correspondence is a transposition of the partition. Now maybe I should write n somewhere in the notation, and small n. So this is the high-straight representation of SLN, of GLN, or GLN. Probably should be in the notation.
So that looks like the notational difficulty for the third lecture. That's a kind of rule, right?
Yes. So if you want, I can put GLN somewhere.
And the sum runs over all lambdas that are acceptable permutations for both?
Yes. So yes. So more precisely, what you will have is that you have, yes. So you have smaller than n rows and smaller than n columns, which is exactly what you need. So here I have to say, which I kind of didn't. So when you go from GLN from SLN to GLN, you allow also the nth rows. because you have a bigger total size. Okay, so this is a statement.
But is it a difficult statement? This
No,
question
I
for
will
is it an elementary? Just to know.
I will explain how to do it. I will almost prove it. And what is nice, I think, is that you can deduce from this the Shurval duality. You remember that the theory of the description of these representations is kind of subtle, right? You have to do combinatorics and so on. But here it is rather nicely realized, this decomposition. Okay, so
What is the role of this anti-symmetric exterior algebra? So, for example, what happens if you take symmetric algebra instead of tensor algebra?
The same kind of statements hold for the symmetric algebra. Actually, Howe first did it for the symmetric algebra, and later for the exterior.
I don't like it in these statements.
Symmetric and askew?
Yeah, it should look like this.
Yeah, there should be, yes.
But wait, you say similar statement, but here the sum is clearly finite,
Right.
but there should be an infinite sum, so you cannot restrict. The conditions would be very different, right?
Yes, yes. So, you know, these are things I'm learning. So, it's probably it also happened to most of you. So when you do a discovery, then you are very excited, and then you start to ask people and to look at the literature and see that it was already done, right? And so you start, and sometimes it's good that you find it the same idea in some different context, and so maybe it gives a new thing, a new point of view of this different context. Then you go on and you find new places where the same idea appears, and then in the end you see that everything was already done by other people. So now I'm in the middle of this situation. So I'm still excited because I didn't find a place where what I will tell you about tomorrow is already written. But this was okay. So. So this you can really so how to decompose a representation of Dln? Well, you have to find the primitive vectors, so the highest weight vectors, right? So vectors of definite degree or weight, which are killed by the positive part of the Eij with I smaller than j. And so to explain what is this decomposition, you have to give in this tensor product, in this exterior algebra, some highest weight vectors for both, some vectors which are highest weight for both these representations, and then from there you can construct the representation. So let me give these vectors. Construction. So you take a basis E1. So let me again be adventurous in the notation. So this En is not good. Ej is a basis of V, which I called, maybe it will be theta, right? And R is a basis of W. So I call everybody E. But the index is another letter of the alphabet.
But you know them by the same letter, so somehow.
Right, so let me put temporarily an N here and an N. Okay. And then so a basis of the tensor W will be EI times ER, which again, but now the position is clear. It is, you don't need to specify, but let me write it in very small font. And so let me, to simplify, call it, I don't know, ER. And now you put these vectors in a table. Right? E1, N1, capital N and small n. Okay? And now to find the vector corresponding to a partition, you draw the partition, the Yang diagram on top of this table. And some is inside and some is outside. And you take the wedge product of those inside. Okay, so the highest weight vector. For SLN, for GLN of weight, lambda and for GLN of weight. Lambda transpose is a wedge product, is a wedge product of EIR, where ER is inside lambda. So maybe it's better to write an example. E11, E12, E13, E14, E21, E22, E23, E24, and let's, I don't know, take this diagram. Then you will take E11, wedge E12, wedge E13, wedge E21. But this you can rewrite also up to sign as you collect first the vectors which have one is a second place and
what E21, right?
E21, yes, thank you. And then 2 and then 3. So now what is the weight of this vector? So the weight here, maybe GLN weight. The torus of GLN are diagonal matrices. And so here we'll have weight. The first eigenvalue will be 3, because this appears 3 times. The first index corresponding to G capital N, which is 2 in this case. And so this is weight. Three, 2, or GL2, 3, 1, sorry. If you look at the first index, you have 3 times 1 and 1 times 2. And here you have the second index, you have 2 times 2 and 1 times 2 and 1 times 3. And this is weight 211, I guess, for GL4. So this is N, and this is small n. Sorry for those on that side. We rewrite that for GL4. And this is a transposed, right? So this is 3, 1 and 2, 1, 1. Okay, so this is the construction. And so and these are all the diagrams that you can draw inside this n by n box. And then you have to show that there are no others. But I haven't done it, but it's not difficult because the Eigen Spaces are, the weight spaces are all one dimension. Just checking. Straight vector.
And it's clear that this is highest weight, or?
Sorry?
Is it clear that this is highest weight? Or?
Yes. Because it's similar to. So if you have, for instance, if you have, as we saw before, if you have wedge k of v,
I see.
it's highest weight E1 up to dk. So the fact that. So if you want to act with, but maybe we'll see it more explicitly later. So if you act with a higher diagonal, higher triangular matrix, then this will be mapped to 0 because indices cannot be repeated. And similarly here, since for the first index, the increasing sequence, I think you can check it, but I think we'll see it more explicitly in a second. So what does this have to do with the Shurval story and to the decomposition of the tensor product? The thing is that if you have, if W is equal to Cn, then you can write so more precisely, I should say that this is V times E1, and this is V times E small n. And then I use the first rule with the wedge. You see that you have a tensor product of exterior algebras. And the action is a little subtle, but what you can easily see is the action of the torus. So the action of the torus GLN is diagonal, right? So it will scale E1 up to En. So what this means is that the decomposition E1 times small nv is a decomposition into Weyl spaces for GLN, GL small n, and so I don't know, if you have a torus element x1 up to xn acts with weights. K1, Kn. So this is at the eigenvalues. So x is mapped to x1 to k1, xn, kn. So this is the action on this. So you write your tensor product exterior algebra in this decomposition, and you write. The weight spaces are the irreducible representations. Explain how to recover the Shurval duality from that story. So here you have to notice that the action of this dual GLN is mixes the thing, right? So it is not that GL small n acts here. So GLN will change the weight, and so it will mix all these factors. But and so, but the Shurval duality you want to take first of all k1 equal to kn equal to 1, and you want to preserve that. And but what happens is that there is a subgroup of this GL small n symmetric group, the Weyl group, if you like, which acts. Let me explain that. Which preserves this weight space. Right, so this I explained. This will be Shurval revisited. So first, there is a remark that Z, so you have a central element, you have central elements in is the center of GLN, so acts as Z to the lambda, so Z in the center acts as Z to the lambda on this V lambda tensor, V lambda transpose for both GLN and GLN. So I think you have two you have Zn and Zn. So for both of them it is the same thing. So this is the size of this, but of course the size of the transposed is the same as the size of lambda. Okay. So so what is this V tensor V? So it is okay. So it is the subspace of GLN weight, small n weight 1, 1, 1. So it means that the Z acts, so it means that the Z acts as Z to the small n, and it is zero weight for SLN, the subgroup SLN. Subgroup SLN, it's ratios of weights, and so it acts trivially. So it's really the zero weight space, except for this, which will tell you the size of the partition. And so it means that that this is in this decomposition we can see it as V lambda, this for SLN, V lambda transposed. But here we have to act on the zero weight space for SLN. So this would be zero weight space of SLN. And we also want that Z acts like that, so we have to sum of the partitions with n boxes, lambda equal to n. And of course, the group GLN will not act on the zero weight space, but the normalizer of the torus will act there. So here you have an action of the Weyl group and an action of Sn, which is the normalizer of the torus, the Weyl group. Right, so you realize this representation theory of Sn as the action of the Weyl group on the zero weight space of highest weight representations.
So does each of these representations have a zero weight space?
No.
Doesn't that give you additional constraints on lambda then?
Sum of lambda equals.
Let me see, so.
Sum of lambda equals 3.
sum of lambda equals to.
Otherwise, the Weyl space doesn't exist.
So you mean this, right? This is sum. Right. So this guarantees the existence of a. I think this guarantees the existence of a high switch.
That means that it's zero weight. Yes.
Right. So, from my point of view, at least, and also for then when we discuss star matrices, it is useful to be more of a physicist here and give a more explicit description of the action of these groups.
The length of the answer, how is it in the general case? Nothing far right. If the weight is non-zero, then what? You would get those multiplicity spaces, which a priori will be some huge spaces, and then what? What do we do in this more general case of how? So you now selected this weight of GL small n. This will correspond to this tensor product of wedge products, and then what? No, I mean.
This is to recall.
Yeah, right. But in the
you want to use this for something, right? Is that what you are?
I think the question is, what's the answer to the question you posed?
Yeah, right. We want to you said we want to generalize it in this product of wedge products. But then here it was very special that on the zero wedge space the normalizer was acting, and then.
Right, but you still have the description, right? You still have this decomposition. Then once you have the decomposition into irreducible representation, you don't care so much about the existence of a group.
But this zero weight space now it doesn't have a structure. It's not a representation. If it's not a zero weight, it's not. At least it's a priori not a representation of anything reasonable.
Right, but it's some weight space of your.
You mean, so the description is you get a direct sum with the multiplicity being described as the weight space, a certain weight space inside
It's
this.
explicit description of the multiplicity space. Well, you don't have a group acting on it, but maybe you don't care so much. Is that right? Maybe it's probably also a question whether one can, there is some kind of subquotient of the group which acts on that side. But once you have the decomposition, you have a description of the multiplicity space. This is what we want to know. Right, so to have a more explicit description of the action of these groups on this exterior algebra, it is useful to use formulas. At the end, it will be also the goal will be to understand those R matrices for fundamental representations. Maybe let me say some motivating goal that we have. Okay, so the motivation was to compute R matrices for GL infinity on Fock spaces. And Fock spaces are obtained as some sort of limiting limits when capital N goes to infinity of these fundamental representations. And so to be able to give a formula for this R matrix, what you need is some description of these finite R matrices in a stable form that do not depend explicitly on capital N. So it's useful. Okay, but we will see that. So let me talk about fermions, and this will also give some explanations of some previous talks that we've heard. So, right. So now we want to view this as a Fock space now. Representation of the G.Felder algebra or canonical anti-commutation relations. So probably this is well known to everyone, but I want it to be, should be a school, right? So I should teach that. So let's define some operators, psi I star on this Fock space. And psi I star of alpha is theta I of alpha, and psi I of alpha is a contraction, is d over d theta I of alpha, and this is a graded derivation. J is delta ij, and d over d theta I of alpha wedge beta is d alpha over d theta I plus degree. Okay, and then this object obeyed the canonical anti-commutation relation. Really, in the language of physics, you say that one is a vacuum vector, one in wedge 0 of V, and then a basis is obtained. So this is killed by these annihilation operators. And the basis is obtained by taking creation operators on these vectors with order. So psi star square is 0, psi star square is 0, psi square is 0. So you can do this. Okay, so this is a kind of physics notation. And then you have an action of Dln. Maybe I will not say much. Right, so the action of Dln is given by psi. For I different from j, so you have to do something for I equal to j, but this generates the algebra, so I don't need to specify. Okay, so this is, you can verify that this is the case, and in the exercise there is a professional way of reducing this. And
So what goes wrong for I equals to j?
I don't think much goes wrong, but so if you do the commutator of
Nothing goes wrong.
Add or subtract 1/2.
yeah, you have to subtract 1/2 or something.
Okay, you have the normal one already somewhere.
Yeah, normal. Okay, so this is a very standard story, and so using this is a kind of safest way to check, for instance, those vectors are high-straight vectors because you can commute and okay, so and maybe the remark is that Dln is really a subgroup of O2n. Because you also have some other quadratic generators that you could add. And on the whole, they give some kind of orthogonal group. And so, explain tomorrow. So maybe just the remark is that to finish is because it was in my abstract, so I need to tell about that. So in my process of finding all the places where was discovering was already done, I first, before finding the paper of Howe, I found the paper of Yang and another author, which and probably Zhao in the 70s, where they considered the Hubbard model. So there, the physical model is you have some lattice. So they consider a higher dimensional lattice, 3-dimensional. We do it in 1 dimension. And suppose that on each lattice site you have a fermion, which can have spin up or spin down. Or some sites can be empty. But you cannot have 2 fermions with the same spin at the same site. Moreover, you have a Coulomb repulsion, so the configurations where 2 electrons stay at the same site should be penalized. So there is a model for that, which is a Hamiltonian on a Fock space. So you have a Fock space. Now you have a tensor product. So you have psi I sigma. So here you have a lattice, say 1 to n, but you can also do it in higher dimensions. And so I is from 1 to n. And sigma is up or down. And psi I sigma star is a creation operator for an electron at the I star who spins sigma. And so we have and then there is a Hamiltonian, which is sum over I and sigma of psi I sigma star psi I plus 1 sigma plus psi star I plus 1 sigma psi I sigma plus u times ni plus ni up, ni minus. Ni up and ni down. And this ni sigma is the number operator. So it is 1 or 0, depending on whether you have a fermion there or not. Right, and so u is some positive constant, so this will, so states where you have 2 electrons at the same site are discouraged by this term, something like this. And now, so in the language that we are using here, this would be, you would have a representation of Dln and Dl2, and so here you would have EI. I plus 1 for Dln, and some of the sigma. So here I should have written the formula. So these are actually Dln operators. This is a sum of and this you can also write in terms of Dln operators, square minus Dii, I think. And so this will commute with the action of GL2. So there's GL2 or GL2. And GL2 is given by some I sigma psi I sigma prime, something like, maybe I will call it small e sigma sigma prime. Simulated by this, and here a star. And but actually it really commutes with a bigger group, and this is because of this difference. So you really have an SO SO4. You can also take some linear combinations of these. And Yang, they computed, they used the representation sphere of SO4 to construct a lot of eigenstates out of a simple eigenstates like a vacuum. But, and they proved, I don't know, of diagonal long range orders for those states. And so it had some kind of physical relevance. But somehow there is this same phenomenon appearing here. Okay, so tomorrow I will tell you about some kind of work in progress on first explain the quantum case, which is also known, and then how to apply it to compute harmonic fundamental equations. Okay, thank you.
Well, any thoughts before lunch questions? If not, thanks again.